Thank you very much to the organizers for inviting me here. It's a real pleasure to listen to all the other talks and to meet all the young people here. Yeah, so I'm going to be talking about sort of interacting particle systems on locally tree-like graphs. I'll spend sort of almost half my talk giving you some background as to what is known in this domain, and then talk about our results. A lot of my results are all joint with my two former postdocs, Dan Lacka and Ru Wu, and as well as my graduate students, Ankan Ganguly, who's actually also graduated, and Juniper Cocomello. Okay, you'll see their names come up as we go along. Okay, so what's the context? So of course, we know that many phenomena are described by large collections of randomly evolving interacting particles, which are indexed by the nodes of a graph, and whose dynamic interactions are governed by this underlying graph, which is itself possibly random. So I will always assume that my graphs are either finite or infinite and locally finite, which means the degrees are all finite, the number of neighbors of each vertex. And what is this graph? How is this graph capturing the dynamics? It just says that the particle whose instantaneous stochastic evolution depends only on its own state. We've seen many examples in the last few talks. Okay, and please, I forgot to mention, do interrupt me with any questions at any point. Yeah, I want to make sure things are clear. Okay, so the dynamics of the individual particle can take several forms. It can be a discrete time process, and so it can be evolving like a probabilistic cellular automata. It can be a continuous time pure jump process, which is what sort of classical interacting particle systems are usually, or it could have a diffusive dynamics. I will not be talking about diffusions here. To keep things simple, I will mostly talk about the discrete time, but I will also talk about the continuous time because that's sort of a more realistic model in many cases. Okay, so what's the precise description of the dynamics? So I'll use the standard notation for NV for a neighborhood of the vertex V, and either CLV or V bar to say the V union, its neighborhood, like its closure, and dV is the degree, which is just the size of the neighborhood. Okay, so you want to, let's look at the discrete time setting first. So we fix a graph and we have some initial conditions, which are indexed by this vertex set, right? And then at every time t, I want to denote the state of this particle V at time t. Okay, so the whole thing, for the moment, we can assume it's a Markov process, the entire process. So in general, this transition kernel of xt plus y, xvt plus 1 given xt could depend on all of the variables like yv in every vertex. But since it's locally interacting, it means that it only depends on its own state at time t, right, which was xv of t, as well as the neighboring states. Okay, so that's sort of this saying, this is just saying that it's locally interacting. And so I have to, of course, provide for any model, I have to tell you what form this takes. And so that's some transition kernel going from this state to this state, but it also depends on your neighboring states. So you can think of it as sort of a transition probability matrix that is parametrized by the neighborhood values, right? So you give me a bunch of neighborhood values, then I know how to evolve from Z prime to Z, right? So I have all these sort of interacting particle systems. They're all going by these, I'm going to assume homogeneity, like every particle goes along this with the same transition probability matrix. Yes, please. Yes, I love questions.
Also the neighborhood part myself.
Yes, myself and the neighborhood. Yeah, and typically I will assume that I'm sort of symmetrically depending on the neighborhood for simplicity in this talk. I can allow sort of some random inhomogeneities, but exactly. I can depend on myself and the neighborhood. Okay, so that's why the self is just the usual transition, and then, but I also have this neighborhood dependence. Yeah, great, thank you. Okay, and just because this in a graph could be of different lengths, right? So you don't really know, it's not like a fixed vector. If it was a fixed regular graph, then it would be a fixed vector of some size. But in general, this A will be of any finite vector sequence, right? Finite length, because it's just the neighborhood. Okay. So, I mean, a very simple model is just to have something concrete in your mind, is a SIR model where each state takes 3 values: susceptible, infected, or recovered, which means that it's sort of immune and no longer contagious, and no longer can be, get sick. And then, so every particle will move from S to I and I to R. And the only question is with what probabilities. And the probability that it stays in R is just one, so it's an absorbing state. The probability that it goes from I to R doesn't depend on anything. It just depends on, your recovery rate, which doesn't depend on anything on your neighbors. So the only thing that depends on the neighbors is going from susceptible to infected. And that is sort of, you're saying the probability that you don't have any infected neighbors. And so some parameter betas and rhos that govern this probability. Okay, the details of which. Or you can look at one where, you don't get immune, and you could get susceptible again, and you have SIS, and you have similar structure. The only thing I want to bring to your notice here is that your rates will depend on the number of your infected neighbors and not just on the fraction. Okay, so it will, if the degree is large, then you'll just have a higher chance of getting infected, which is a point that I will make later. So it's not really just looking, because it depends symmetrically, right? It doesn't matter which ones are infected. You only depend, but it does depend, doesn't depend just on the empirical measure of your neighborhood, but it depends actually on the number as well. So it's, okay, that's an unnormalized empirical measure is what you should think of. Okay, or you can have opinion dynamics where you have two particles having -1, 1, and then again, they -1 to 1 flips proportionally to the number of your neighbors who are fraction of your neighbors now, who are the opposite persuasion. Okay, or you could say that I don't look at the fraction, but I look at the majority, and sorry, that's called the majority dynamic. So there are all of these sort of general dynamics, and all of them have this form, right? That you have sort of symmetry with respect to the neighborhood. Okay, so that's the general class. But what is the general setup? In all of these cases, we know if you have a Markov chain, you can represent it, in terms of a stochastic recursion with some IID noises. So we can just think of it in that form. We can put all of these in this form. So every time you have xvt plus 1, it's a function of xvt, that at what its state at time t, its neighboring states at time t, and some independent for every vertex and every time noise, IID noises. Okay. Okay, so you can always represent Markov chains like this. Okay, and so there's some suitable function here, right? Okay, yes. No, please, thank you. The function is deterministic. Yeah. Right, randomness for the flipping probabilities, for instance, for any CDF, you could just have the size being uniform 0, 1 and detect the inverse and then do what you want. Yeah, thank you. It's all very useful to have questions. Don't hesitate. Yeah. Okay. If it's not clear, it's my fault. So make sure to ask. Okay. Okay. So that's the general structure of the discrete time evolutions. Okay. And similarly, one can just do the continuous time analogs. Now, instead of transition rates, right, transition probabilities, you will have jump rates, right? So here again, the voter model, you can S -1, 1, and the jump set is either I go from -1 to 1 or 1 to -1. So there are two types of jumps, right? And here again, it's the same thing. It's just that the rate will be like, if I am -1, it'll be proportional to my neighbors. Okay, so these are just the exponential rate parameters. Okay, so it's the same thing, but it's useful to think, if you notice here, the way I wrote it, I didn't write x v bar of t, which would have been a natural thing to do, but I wrote t and x v bar, where x v bar is the entire process, because maybe I want to look at non-Markovian jump processes as well, right? Like, so in the contact process, maybe my recovery time is not exponential, right? It might depend on the past. And don't worry, it's not too important. This is just to say that the framework allows for that generality. Okay, so I could allow this, and I can capture this by looking at some non-exponential distribution, taking its hazard rate. I can represent the dynamics in this form as a jump process with some rates, if you want to. Okay, so that's all. You just have to keep in mind that, or even the discrete time, we can do it for non-Markovian processes. Okay, so again, you can think of the continuous time jump process as general setup. You can think in terms of those rates, which I will often, or if you prefer, you can think again, it's a family of jump matrices, like Q matrices. And again, they're parameterized by the neighborhood. Okay, clear? Okay, and you can define, we talked a lot yesterday about very interesting things about Glauber dynamics. That also falls in this category. Okay, okay. So yes, I already mentioned this. And so what are the quantities of interest? So this is, of course, well-studied models, right? I mean, it's very classical. There's a book treatises on the contact process voter model of Liggett and Durrett and a lot of other people. So you have this dynamics, you have some initial condition, and you're often interested maybe in the fraction of infected vertices, or you might want to look at the history and say, what's the fraction of people that ever became infected, or what's the fraction of people who change their opinions 5 times, or whatever you want, right? Like you might want to look at empirical measures at the state of time t, right? Or of the entire trajectory, right? Either one you can look at. And, if you prefer not to think in terms of empirical measure with the delta masses, just think of these as averages of nice functionals, right? So you take some functional, the psi could be the indicator function that I flipped 5 times, or it could just be psi could be this. So I just take the average number of ones in the system, etc. Yes, thank you.
Right.
So right now I am doing just finite graphs. Thank you very much, because in fact, that's very good. And thank you. See, I always say it's very useful to have questions, because we will see that this particular thing, what I said so far could have been on any graph. And I did say infinite or, but the empirical measure only makes sense on a finite graph. Indeed. Yes. 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 Yeah. I just, for simplicity, I wrote just, you will see, I wrote just this, but I could look at the neighborhood of this. Thank you very much. Again, very useful question. Yes. Yes. Yeah. So this is, yeah, just to say, this is the graph and this is the initial condition. Okay. Any other questions? Okay, great. Okay, so we want to understand these global empirical measures. So what are the key questions? We know that we have these, typically they're very large graphs. You can, you don't want to just run them in simulations and sort of see what's going on. It's not an efficient way to understand the systems. So of course, what would be unintuitive to everybody except people in this room would be to actually take, the size of the graph to infinity. When large is hard, you take it to infinity, right? Okay, so we do that, and we want to say that, okay, if I look at, I'm actually interested in some finite graph and what's happening, right? But okay, so let's just take it to infinity somehow, take a sequence of graphs, embed it in a sequence. And then can we see that maybe these processes converge to some other limit process that maybe I can, is somehow more tractable? Do the global empirical measures converge? That's often called some hydrodynamic limits or something. And there's no rescaling in time here, but you don't need to, so. Or can one autonomously characterize the limiting dynamics of a fixed typical particle, right? You might want to just know what's happening to me in the system, or what's happening to me and my neighbors, right? Okay, so these are the sort of 3 questions we want to address through this talk. Okay, so that's the problem formulation. And I want to just talk about classical results, like what kind of results can we expect? What do we think we know? So let me look at sort of not the regime that we're interested in, but like what's known in other regimes. So in the dense regime, by that I mean, we can just take G to be the complete graph, as also was mentioned yesterday. So if you take the complete graph on n vertices, right, which was deemed simple yesterday by Will, so I agree with you. So you fix the initial condition on the state space and something, set this xnx. Now I don't have to say gn, because once I know the n, so I'm just simplifying the notation to call it just xn. And then you have some discrete time evolution that I told you about, right, for all these n particles. And again, I said it's going to be symmetric in the neighborhood. So, we can write this f in terms of these average quantities here. Okay, so I'm just going to rewrite this. In this case, I'm assuming that I can just rewrite it in terms of the empirical distribution, just for simplicity, right? Okay, so you have some other f bar, which depends on my time at time t, and then the empirical measure of the neighboring particles, just how many are of what type. That's all it means, right? And then this external noise. Yeah. Okay, so now, why would we expect any limits to hold in this case? So let's try to think, if these were non-interacting, right? So there was actually no dependence on this, right? Then we know, okay, these are just all IID things evolving. Then the empirical measure, just by the strong law of large numbers, what would it converge to? Yeah, it would come, yeah, sorry, yeah, I think you said the right thing. So it would converge to the expectation, because these are all identical, IID. But what is the expectation of the Dirac delta mass? It's simply the law of the process, law of X1. Okay, so if you had no interaction, you would expect this to converge to its law, which would be great. Then, this, would sort of, you would replace it by the limit law, and then, you would have something that might be tractable. But of course, the whole point is we don't want non-interacting, we want interacting. That's the whole point. But what's there to remember is that if you only have this kind of an evolution, then any one particle, the way it influences you, is of only magnitude 1 over n, right? Because it's only influencing you through the empirical measure. So if it's order 1 over n, you expect that to sort of decay as n goes to infinity. So you expect some asymptotic independence. For any finite n, you won't have independence, but asymptotically, you will. Okay. So if f bar is, of course, nice enough and things like that, but most reasonable f. So in fact, that's what the classical mean field limit does. It replaces this mu nx by its limit, which would just be the law of any one particle. Of course, these are also changing with n, but they would just say that if it's close enough, then maybe I can replace it by the law of the limit particle. So you get something like this. I replace this by the mu bar, and mu bar would be the law of this. This should be x bar. Okay. Yeah. And so now you have a sort of closed system. X bar is evolving like an inhomogeneous Markov chain because it depends on time. But remember, mu bar, even though it's a measure, you can just think of it as a fraction. So it's a deterministic quantity. So this thing is something that just depends. So this is, of course, just a Markov chain, right? Because you have x bar t and some external noise for every time. So it's a one-dimensional Markov chain. And then this x bar, this mu bar is something that is modulating the whole thing with time t. Okay? So it depends on its own law. It's inhomogeneous in a special way that its time dependence is not arbitrary, but depends only on its own law. Okay, and such processes, because their forward Kolmogorov equation will be nonlinear, are called nonlinear Markov processes. Okay, but it's not nonlinear in the sense of linear versus nonlinear, right? But it's nonlinear because the forward Kolmogorov. So you can also think of these as sort of measure-dependent Markov chains to make it simpler, or law-dependent. Okay, is that clear? So this is really well understood. This is very classical. I said classical because in the discrete time, I don't know whom to attribute it to. In the continuous time diffusion, it goes back to McKean-Vlasov in the 60s and Oldschlager for continuous time Markov chain in 84. But discrete time is so many different versions. Okay. Yes, please. Okay. So it is a process. You have to think of it, it's like telling you, thank you, but it's the evolution of, it's a random process, which is evolving like any one typical particle will do in the limit. So in this case, it's an S-valued discrete time sequence, random sequence. Thank you, that's useful. So that's why X bar, I have to tell you what it is at t plus 1, t, So X bar is a vector with 0, X bar is 1, X bar 2, X bar t, X bar t. Yes, please. Yes, I'm fixing a whole interval, t, and then letting n go to infinity. Yeah, so not 1 t, but like, yeah, a whole. Anyway, they're a finite number. Here it's countable, so it's sort of simple. But yes, indeed, I'm fixing t and letting it. I'm not doing any rescaling with t. Thanks for the clarification. Any other questions? Yes, please. Here I'm sending n to infinity. I is fixed. So here, of course, it has all the i's in it, this mu bar. Okay, has all the, mu has all the i's in it, mu n, right? Because it's taking the empirical measure of everybody in the system. And what I'm saying is here that any one, because I might as well choose any one, because I can take x1 to be any typical particle because they're all exchangeable, which means that the law of the whole collection is permutation invariant, right? That's what exchangeability means. So you have this X bar you should think of as just the evolution of a typical particle. It's approximating the evolution of any one particle, in the limit. Yes, please.
You took like a pair of particles, does it look any different? Does it look like
Excellent question and very useful. I'm going to say a little bit about that in the next slide, but remember my very pertinent question, and the reason the arguments that I gave for why this holds is that I expect these particles to be asymptotically independent. And indeed they are. So that's actually also crucial. So like I said, that this is a Markov process, and the proof, like I said, if it was non-interacting, just a strong law, but in the general case, you still have this asymptotic independence, which is also called propagation of chaos. And I'm assuming that the initial conditions are IID or exchangeable for that to happen. And then you have this mu n converging to a deterministic limit. And if it converges to a deterministic limit because of the asymptotic independence, that has to be the same as the law, and so far you get everything. Any question? So from this, you might think, okay, this is not closed, but it is in fact because you can write an equation for the law of the system, which will just be a nonlinear equation. You can solve that, then plug that mu bar t in, and you get a inhomogeneous Markov chain. Any questions? No, please do. Yeah, I mean, this is important for what's coming to come. Pardon? I is for each vertex. Yes, because I switched, because we're doing just 1 to n, I switched from I to n in an earlier slide. I said that we're just going to use I instead of V, because we're doing the complete graph. Yeah, thank you. Yeah, just complete graphs are just 1 to n. So that's why, otherwise it would be the size of the vertex, size, set, and everything. So thank you. Excellent. Any other questions? Okay. And so essentially what you're using is the asymptotic independence, and then you used exchangeability, and then some minor continuity properties of F bar, right? Because I sort of said I could replace the mu n here by mu bar. That's only true if F bar has some continuity. Clear? Okay. So of course you have to prove some tightness and things like that, but this is really the basic thing. Okay, great. And this, by the way, I mean, if you haven't seen these mean field limits, they're ubiquitous and they're all over the place, both in applied settings as well as, everywhere. Like, so if you've seen the Ising model yesterday, the Curie-Weiss model is sort of the mean field version of that. And that was, sort of easier to analyze than the Ising. And these, if you look at any sort of interacting particle systems that arise in application, the first thing people will do will say, okay, let me just write down what the mean field model looks like, mean field limit, and then, try to get some insight into what the system is doing. Okay. So given that, so similar results hold in the continuous time setting. Instead of a recursion, the law of the process is given by some ODE, nonlinear ODE. Okay. So remember this gamma was that transition probability matrix that was indexed by laws, right? Local laws. But now here the local law is actually the same as the global law, because I have almost everybody in my neighborhood because I'm on the complete graph, right? So that's an important thing to say, that in the complete graph, the local evolution is what I plug in here is the global evolution, and then I get this. Okay. You don't need to know exactly why, but this is really just the same thing. Just want to say the analog holds. And you get a nonlinear ODE rather than a nonlinear recursion. Okay, so the answer to the key questions that we asked for the case of the complete graph is yes, the x1n has a limit. And it's a consequence of the exchangeability, by the way. Just the fact that there is a limit, not its characterization, just follows from high-level things about exchangeability, right? We have experts on exchangeability in this audience. Okay, and then does the empirical measure process have a limit? And yes, we showed that, and it is deterministic, and it coincides with the law of a typical particle. Yes? And that's a consequence of the asymptotic independence. Okay. And then does the law of the dynamics of a fixed or typical particle can be autonomously described? Yes, we said, because we have this, the local the neighborhood is the same as the global, and we got this nice nonlinear ODE or nonlinear recursion. So we've answered all of these in the affirmative, or rather we as in we know that it has been classically answered. Okay. Okay, great. So this is a really nice case, simple case. So now, of course, the question is, these mean field approximations, if you pick up any paper, they're just, you usually want to use it for some finite graph, right? And okay, occasionally it might actually be a complete graph, but most of the time it's not a complete graph, it's just some graph. And you sort of assume that, it works. Now, it turns out that these things also you can prove over the last, 8 to 10 years, the same intuition that I gave. I told you if you have a lot of neighbors and those number of neighbors is going to infinity, then the influence of anyone on you is 1 over the degree. And if the degree of all vertices is going to infinity, you will again get asymptotic independence. You don't quite have the exchangeability, but everything else goes through. You would expect a mean field approximation to hold. And indeed, it's been proved under various circumstances that even when the degrees go to infinity, as n goes to infinity, minimum degree, and then, you get the same thing. But now what about other graphs? I mean, many real world networks are actually sparse. That means they sort of have uniformly bounded degree, right? Like if the population of your city goes, it's not like your friend circle is growing proportionally, right? So, okay, unless you're a real extrovert, right? So, okay. So if you have a discrete time SIR process on the ring, let's see how it does. So if this is just blue is just a simulation, and the mean field approximation is, this is just the plot of probability being healthy versus time. Okay, so we can see that the mean field approximation does okay in the beginning, and then it does really quite badly. Okay, which is, the ring is not at all dense, so it's not a huge surprise. But there are other, you could do the similar things for trees, and it's sparse graphs. The mean field is really not that good. Okay, so that and this is a continuous time Boto model on the 3 regular tree. And again, you see that this is now the probability that one person agrees with exactly 2 neighbors, just something that takes into account correlations, as Ahmed asked. And you can see that, and thanks to what you asked, we know that the mean field will assume that neighboring particles are independent. And so that's going to do really bad with any sort of correlation type question. And you can see that. So this is just staying constant, whereas, this is the real evolution. So of course, physicists and other engineers sort of know that, okay, in this case, I shouldn't use the mean field because I know that they're strongly correlated in the limit, right? So I will use some sort of ad hoc approximation and sort of try to write down some equations for how the correlations evolve. And that's just ad hoc, that's no limit theorem. Those are called pairwise approximations. You can just run them, and that does better in the beginning, but then it still does badly. Okay. Okay, and you can, generate a lot of these plots, but this is just to see, so you're not getting accuracy. So this motivates, and maybe if you go on, maybe it'll be okay, but how do you know when you're good and when you're not? And you want a rigorous theory to understand, what is actually the limiting marginal dynamics or the limiting empirical measure, right? If you can. Okay, so that's the goal. We want to first really look at uniformly sparse graphs. So in the literature, when people say sparse graphs, they sometimes also mean graphs whose degrees are not growing proportional to n, but are going at a slower rate, like log n or something. Here in this talk, sparse graphs will mean uniformly bounded degree or average degree. Okay? Okay. So the first question to ask is, what is the nature of the asymptotics? Right? In the case of the complete graph, we simply took the number of particles to infinity, n. And here, clearly, that's not going to be a reasonable model because you care whether you're on, if you're doing, your local neighborhood matters, right? So you really care whether you have 4 neighbors or 3 neighbors or 1 neighbor. It's going to matter because each one has a strong influence. So you want a notion of, like I said here, we know this, and dense graphs are sometimes, and they're still not fully understood, but have this nature, and we want to understand the sparse graph. And we have this nice notion, which was mentioned many times yesterday, but I don't think it was actually defined, so I'll just go through it quickly, but we have this Benjamini-Schramm notion of convergence that does exactly this, which is preserve local neighborhoods of graphs, right? So this is just saying that for every finite k, if you have a large enough n, which such that the k neighborhood of the rooted graph is isomorphic to that of the limit k neighborhood of the limit graph, then you say that you have convergence, local convergence. And you can metrize this, and it becomes a nice space, Polish space. So you can talk about random elements on that and weak convergence. Okay. Okay, yeah, so then you can also, but now, when we have dynamics, we also need initial conditions to converge, right? You can't just have some arbitrary initial conditions for each n. So you need not only the graphs, but you need graphs marked with initial conditions, right, to converge. So it's naturally to ask about marked graphs, which all I mean is that every graph, every vertex also has some value, which is taking values in the space. And then this is a nice notion of marked convergence of marked graphs, which is just exactly what you would expect, which says that for every epsilon greater than 0, there's a large enough n such that you have some isomorphism, because that we know the graph itself has to be firstly locally converging. There's some isomorphism such that then the local neighborhoods, the distance between the marks is epsilon close. Okay, so it's just the most natural definition you would put down. Okay. Okay, and so this is the notion. And so what we would want to understand is if the initial conditions converge, then would the graphs marked with the trajectories, which would be these sequences, as Lewis asked, these random trajectories, would they also converge locally? Right? That would sort of be the question that you would ask. So really, this question is about marked graph convergence. Yes, please. Yes, B is the name. Maybe I went fast here. So BK is a ball of radius K at root. Yes, for every K, you choose a large enough N. So the N can depend on the K, but it has to be true for every K. Yeah, it has to be. So no, you would think it's small, but you need it for all K. Yeah, because yes, large implies small. Yeah. Okay, great. Yeah, so every, it's sort of like uniform on compact kind of thing, like it's that kind of a notion, which is exactly, we say locally local convergence. Okay, so it's like looking at the graph from the point of view, of course, these are rooted graphs, because otherwise you cannot define what is BKG, right? So these are rooted graphs, and the roots could also be random in what's to come. Okay, so just an example of just graph. So the cycle graph locally looks flat, right? Like it goes to a line. Okay. But now you can, like I said, that was a notion of convergence for connected graphs. Okay. But sometimes we would like to also consider maybe possibly disconnected graphs. And so this is a natural just extension. So if you take a finite graph and let CVG denote the connected component of G that contains V, then a sequence of finite graphs, Gn, converges in distribution. So now these are possibly random graphs, converges in distribution in the local weak sense if they're average, that, these averages we were interested in. But this function is now of the component, the entire component. So it's on graphs or marked graphs that you would have it. And that goes to this. Okay, so just some convergence like that. And this is, of course, convergence in distribution. And there's also this convergence in probability, which is a bit stronger. Don't worry too much about that. I will just sort of mention this in the side as to why that distinction is important, but that's not the main focus of the talk. I'll just say something about that. It's a slightly stronger notion, but okay, just to give you an idea of what this component empirical measure is, because we're going to use it a lot, right, is this following. So you have this, so this is another way of saying what I said was this component empirical measure is an empirical measure which puts mass on various types of graphs, rooted graphs. Okay, so it's a measure on rooted graphs, and the space of rooted graphs we call G star. Okay, so it's a probability measure on G star. It's a random probability measure on G star. Okay, and so just to tell you what I mean, I take a uniform root. I always assume that my root is uniform. So this is a good way to see, like, here's a graph with n vertices. And now if I take this vertex, right, then my graph will look like this, because this will be the root. And then the rest, the neighborhood only looks like this, the whole component. And it will also be the same if it's this vertex, because up to isomorphisms, I don't care about the labelings. The same. So this is with probability 2/7. The component empirical measure will put mass 2/7 on an object like this, 2/7 on this, which comes from taking this as root. If I take this as root, you can work through it and see that you get different components. Okay, so that you have a clearer idea of what this component empirical measure is. And so really what we're asking is that this converges weakly to some measure on G star, right? That's local convergence and distribution. Okay, okay. Okay, and so now we can talk about random regular graphs. And so in terms of this notion, a random regular graph converges to the infinite regular tree. And this is sort of non-trivial because again, okay, in the cycle, it was easy to see that the cycle converges to a line because the cycle is getting larger and larger, so you don't see the cycle in the limit. But here, it's not completely obvious that in a random regular graph, which is like K, so a uniform random regular graph is simply, you take all d-regular graphs on n vertices and select one uniformly at random. Okay, that's the random regular. And that certainly has cycles, and it has even short cycles. But what the content of this theorem, this is due to Bolobach and McKay, is really saying that when viewed from the probability of a random root is not likely to see a short cycle with high probability as n gets to large. Okay, that's what it's saying. Okay, and then we can look at our, another standard Erdős-Renyi graph, which is the n vertices, and each pair of vertices are connected independently with, let's say, some C over n or P over n, right? So it's a sparse graph. So here I made it more general and allowed NPN to converge to P, but you could think of it as just P over n. And then that converges to a Galton-Watson tree, which is a tree which is rooted here, and it has a random number of offspring, which is Poisson distributed and go on. And if you, yes, you had a question? Oh, no, okay, sorry. No problem. And the Poisson comes from the fact that, if you think of the number of neighbors of this is sort of like a binomial, and then sort of the law, rare event, small law, or whatever it's called. Yeah. Okay. So there are many, many other examples, such as for those who know in random graphs, something called the configuration model that also converges. So the configuration model is something that people very much use because they say, if I have a graph and I look at the degree, empirical degree distribution of that graph, and then I assume that there is a sequence of graphs whose empirical degree distributions converge to some limit, then I get a configuration model. That's, if you choose it uniformly at random for all graphs that have that kind of degree sequence, then that converges also to a UGW tree whose offspring distribution is that limiting distribution. Okay. And I'm saying UG because there's some, here it's Poisson and everybody else has Poisson. In another case, the remaining ones have a slightly changed degree distribution, which is called a size bias degree distribution. Okay, I won't get into that too much. That's important, but not for the level at which I'm explaining now. Okay, so the point is that many random graph models that one is of interest converge to random trees. That's the point. Okay, so now we at least we've just talked about, okay, what notion of convergence we're asking. So now at least we know we're going to ask if the graphs marked with their initial conditions converge locally weakly to a limit, then do the graphs marked with the trajectories associated with that initial condition and the dynamics that you were given also converge to a limit, right? That's the question. And if so, all the questions we have. So let's look at the first question was, again, the discrete time process. And does Xn and Gn mu Gn converge? So it turns out if Gn and Xn converge in the slightly stronger sense, which all the examples I gave you do satisfy, in probability to Gx, then indeed the trajectories also converge in the strongest sense, in the local weak sense, to the dynamics on the limit graph. Okay. Okay, so maybe that's not like super surprising, but okay, it's true. But what is the global empirical measure also, as you mentioned, it cannot converge to a limiting global empirical measure unless the limiting graph is finite. So if it's infinite, then it converges to the law of the root particle on the limit graph. Okay? You want to think of the root particle just like we said earlier, typical particle, right? Where we said X1 earlier, so it's like that. Okay. And so we see that in fact, so, okay, this also holds for non-Markovian dynamics. So I should say that there were some earlier specific discrete Markov processes on directed graphs. There were some other results as well before this work with Dan Lacker and Yo Wu Wu, who looked at sort of page rank model, like specific models, and not really identifying this convergence in probability, but using it sort of implicitly. Okay. Okay, so, but then you have this convergence of the root particle with the same dynamics on the limit graph. Okay, so this is the same structure as in the mean field model, right? This empirical measure is converging to a deterministic limit, and that deterministic limit is coinciding with the law of a typical particle. So that's quite surprising because we know that sparse graphs look, the dynamics and everything is different, but this is still holds. Yeah, I will skip the proof for now, but I intentionally kept it here in case somebody wants to know more about it later. Okay, so when the same thing holds for jump processes almost, but there are subtleties, because in that case, you see, you have to say that you even have a limiting process well defined on the limit graph. When you have an infinite graph, it's not completely even obvious that you have a limit process. Why is that? Because how would you construct a jump process? You would just try to order all the times of the jumps and then just sort of, recursively progress. But what if there's, you have infinite vertices and your dynamics may depend on what all the other vertices are doing. And if the times accumulate, then you don't have a first time to jump. So this is sort of saying coming in from infinity, and you can have non-uniqueness or you can have blowing up problems. And so in fact, we have an example of just a tree graph where you can have, if the growth is too fast, then you can have non-existence of a very, very simple model, but including contact process. So you had to put some, reasonable conditions on the rates. But remember that I told you, like in the contact process, that your rates should be proportional to the number of your neighbors, not just fractions. So you cannot assume your rates are bounded. Okay, so we assume that there are some growth rates that they can be arbitrary as a function of your degree. So the CK is not like linear in K or anything, it can be anything, but it has to be fixed with the K. So you have some constants and you have some bounds on the rate. So these are pretty reasonable, satisfied by all these models. If you have this minor assumption, then GN converges locally to GX if it converges, in the same way. And you need this certain property on the limit graph that allows you to say that you have existence. Okay, and we call that, it's a sufficient condition for that is something called finite dissociability, which I can tell you later, but I want to get to sort of some other things, and then I can come back to this if anybody's particularly interested. And then you can say that this converges. And all of the graphs that I mentioned are finitely dissociable. So I could have just stated it for Galton-Watson trees with first moment bounded. Okay, and it's true for all bounded degree graphs, but that follows from classical results of Liggett or Harris or things like that. But this is really trying to say when you don't have uniformly bounded degree graphs, can you still get existence of these interacting particle systems? You have to do more work. Yes.
So mu is the
yes,
right?
yes,
So
yes.
this is measure at a single time?
No, so remember that I also looked at the empirical measure of trajectories.
Okay.
So this is and so this is the law of the entire process. The root particle, like, so if it was a discrete time, it would just be some random process in Cadillac paths. So the law would be some probability measure, like, like a Poisson process or some other point process. And this would also be, it would have been a random such process because it's, if you prefer, think of it just at T, and this is also true at T, if that's easier to explain. But this also allows you to say that, if I want to understand things about the trajectories, like functionals of the trajectories, like the supremum of the trajectory over time 0t, you can also just look at this particle, look at its supremum, But if it's easier, just think of this evaluated at a fixed time, and this also evaluated at a fixed time. Then it's simpler objects. Yeah, these is just a probability measure on the state space. This would also be a random probability measure on the state space. Yeah, thank you. Okay. So this is exactly the same result, except with an additional condition on the limit graph. Okay, so again, I intentionally said I'll put the proof there, but then we'll come back to it later. So that was just saying that the limit exists. And for the hydrodynamic limits, again, if you can also show that the empirical measure converges to this. Yes, it does. It requires more work, but okay. So now we have this first two questions are answered in the sparse graph case. In quite some generality, and you sort of have the same thing as the mean field. I'll tell you a little caveat at the end later that it's not always true if you don't have this convergence in probability and you have something weaker, but we can talk about that later. And generically, you have this, which is really nice. But remember, the whole point is not to prove limit theorems, but is to understand the dynamics of the n system. And if you are a skeptic like I am, then you're going to say, how does it help to approximate the empirical measure of an n particle system by the marginal distribution of an infinite particle system? How am I going to get hold of the empirical distribution of an infinite particle system? I mean, I have to simulate the whole thing and take the marginal, right? So you're not helping me in terms of understanding it, unless, like in the mean field, you give me some way to characterize this limit autonomously, right? Okay. Okay, so that was about this. So now we want to know, is there an autonomous description of the limiting dynamics of the typical particle? Okay. Now, remember what we did in the mean field case. We said, okay, this dependence on this is symmetric. So we can replace this by the global empirical measure. And then we know that that has a limit, and then we sort of did nice things with it. Now here, even if we know the global empirical measure has a nice limit, these will be only local empirical measures. Yes, and they will remain stochastic till the end. And I don't know what they are yet. I only know the global empirical measure convergence. So knowing the global empirical measure does not give me immediately this property. Okay, so we have something completely new that we have to do. I mean, all of these things were sort of different from the mean field case, but really we don't know what is the new ingredient. So one thing we thought about is, and that's, thanks to the, previous lectures, we know that if you had static systems, and if you had static systems on trees, so this is a high dimensional dependent system, right? If you have static systems on trees, then you can do some sort of recursions to try and understand what marginal distributions are. So you might hope, but that's only true if those static systems are Gibbs measures or Markov random fields with respect to that graph, with that tree graph. So you might ask, is this dynamical system, the trajectories, okay, or the marginals at time t of the process, is that a Gibbs measure? Okay. So it turns out that it's well known, and this has been studied in many spin systems and diffusions, etc., that if you start even from IID, so you take Glauber dynamics for something like the Ising model, and you start from IID, and you know you're going to stationarity, which is a nice Gibbs. So you would think there might be some nice little progression to becoming Gibbs, right? But in fact, it can behave quite strangely for even very reasonable models. You can lose your Gibbsianness. These are called Gibbs, non-Gibbs transitions and locally Gibbs, things like this, okay? So you will not have your marginal distributions preserved. You will not have this Gibbs property. So it will not be a Gibbs measure on the tree, even if I start with IID initial conditions. Okay, so that's really sad. But then you might say, well, but I'm not interested necessarily in just marginals. Maybe if I looked at the whole trajectories, right? Because I want to look at it. Maybe the trajectories will be, Gibbs measures with time. Oh, it turns out that they are not either. I mean, I don't have enough time to give you a spurious argument to convince you that it is and then tell you why that's wrong. Okay, but that's really useful. You should think about that a little bit as to why the trajectories, because this is locally interacting. So let me maybe tell you what is a Markov random field. So so I have this and I want to give an autonomous description for this, okay? So it turns out that I want to somehow, when we came to this point, it was like, I don't have asymptotic independence. I don't have those things that I had. So maybe I should exploit some conditional independence properties, okay? Like think of it as a graphical model, think of it as a Markov random field somehow. But it is not a nice one on the tree that will allow me to say, okay, I'm done, I can apply the other. So let me first tell you what the answer is, and then I'll tell you how we use the conditional independence. So it turns out that using conditional independence properties and several other things, which I will go in detail about, we are able to provide an autonomous description of the marginal dynamics of the root neighborhood on a Galton-Watson tree. So not just the root, it turns out that not the root, but the root and its neighborhood is the right thing to look at, both for the question that Ahmed asked, because you want to know about correlations. It's not enough to just look at the root, but also if you want to get an autonomous description, you should be looking at the root and its neighborhood, not just the root in this case. Okay, and so what is the kind? I will tell you sort of what is the spirit of that dynamics. So again, it is like a So remember that I'm looking at this limit particle. I'm telling you how it evolves, right? Remember, I did the same thing, this nonlinear. So here, I again have this xvt plus 1 equals zx. X here now is a typical particle, the limit, right? Okay. That will be, again, I will look at where I was at time vt and what's the probability I go to z. And then remember, it's parameterized by all of these local neighborhoods and things like that. But here, it's not just parameterized by the local neighborhood, but it's actually parameterized by the law of the entire past of the local neighborhood. So even if your original system was Markovian, the marginal dynamics is non-Markovian, okay, because of this strong correlations. Okay, so it turns out, so these are some transition kernels, but that depend on the history up to time t. Okay, so that's the overall. So it is, again, a nonlinear Markov chain, but path dependent. Okay, yes. I will tell you in a minute. I will tell you exactly. It's not obvious at all, right? Yeah. Okay. So let me tell you now. Simplest case, marginal dynamics on the line. And how do you do this? So like I said, you can think of these as this coupled. So now let's just look over here. I'm relabeling no V's now, and I'm going to -101, putting it on the line. So now I just want to get an autonomous system of equations for the -101. Okay. So I'm wondering whether, so here I actually tell you how it goes. So maybe I will actually tell you the proof before I tell you how it goes, and it'll make more sense. Okay. Yeah, I'll just be 1 minute and it should be done, yeah. So what I do is we prove that this is the paths form what is called a second order Markov random field, okay, which means that if I condition on, and a global one at that, so I won't go into the details, but what it means is if I condition on these two, then this side is independent of that side. Okay, so not one, but if I condition on two, then I get this independent. How can I use that? Okay, the first thing is I want to understand the transitions of this. In order to understand the transitions of this, of course, 0 I can evolve nicely because I know my 1 and -1. But my -1, I need to know the conditional distribution of -2 given the paths of all of the 1, 0, -1. If I know that, I can evolve. If I know the paths of them and their law. But the thing is, the conditional distribution of this given these three is the same as the conditional distribution of this just given these two by the conditional Markov property and the random 2 Markov random field. Then you have symmetries on the line, which says the conditional distribution of this given these two is the same as the conditional distribution of this given these two. But I know that because that's autonomous in my system. And that's how you use it to evolve. And that's how the path dependence comes in, because you do not have the conditional Markov random field with respect to marginals, but only with respect to paths. Okay, so this is just telling you how you can just algorithmically run this thing that I told you. And I will end with that. Yeah, this is again, what were the key ingredients of that proof. And I just want to, so of course, those were non-Markovian local equations, but I can sort of just willy-nilly make, there's an obvious way to Markovianize it, which is just take the conditional expectation, which is obvious, that is ad hoc. This writing down the Markov local equations is ad hoc at this point. But it turns out we would like that because then it's computationally nicer, right? But here, so if I do the discrete time SIR model, it's really working really well. And the reason it's working really well is, in fact, it's exact. So even though in general it's non-Markovian, there are several types of dynamics for which the Markov equations are really good. And with Juniper Cocomello, we showed that they're in fact exact, and you can use these ODEs to analytically prove that the mean field always overestimates the outbreak size, for example, in the SIR model. And you can get various other things. You can use the ODE to analyze various things about, the SIR model analytically rather than, through simulations. Okay, I won't go into that. I will just stop with, but how do the Markov local equations fare for other models? So it's not exact for the contact process, but it is in some regimes. And so that's an open question to understand better how much non-Markovian is needed when the original system is Markovian. But when the original system is non-Markovian, then this is a huge reduction, right? For the marginals, you just get a non-Markovian system again, but it's a much reduced dimension. When the original system is Markovian, of course, now you get sort of this trade-off because you get a non-Markovian system. But it turns out that in many systems, that's an open question. And there are some results we have for equilibrium behavior, which may relate to some of Chris's work. And yes, you can actually, if you run Glauber dynamics, you can see the phase transition appearing. This is Glauber dynamics of the Markov local equations, which are exact for reversible systems with stationary distribution on the tree. Sorry, I don't have time to go into those details. So I will just end with, sort of saying that this is just the tip of the iceberg. Like mean field limits have been around for like 50, 60 years, and people are still doing various things. We're just sort of a little bit of insight into one way of trying to understand asymptotically exact marginals and empirical distributions of sparse graphs, but there's a lot more to be understood in terms of long time behavior. Like as you asked, there's a finite time results, except for the Markov local equations work with Ganguly, which I didn't go into. And then the question that I didn't mention, I only told you what's happening on the line, and I use symmetries and translation. What about on the UGW tree? You don't have translation symmetries, so you use unimodularity there as your symmetry, and it's quite involved to show that you can use that to get the Markov local equations. But then the question is, can you do this on other graphs if you have the right symmetry properties and the right conditional independence properties? Can you go beyond tree limits? Because there are some random graph, going beyond lattices, there are other random graph limits which are not necessarily completely tree-like. And understand these things more. And I don't know if there are other applications that come from ergodic systems as well. I'd love to hear. Thank you very much, and sorry for going a bit over.
Or maybe one or two questions.